Hello everyone, in today's class we're gonna continue on with chapter 3. Today's lesson is the overall heat transfer coefficient, but before we start the new lesson, we'll just take a small amount of time to review what we did so far in chapter 3. So what we did so far in chapter 3 is that we focused on heat transfer through conduction in different models. We looked at a plane wall, a cylinder for pipes and tubes, and we also looked at convection heat transfer. We took into consideration in all these models the resistance. So for conduction resistance, we looked at a plane wall, and we found that the resistance equals 2L over Ka. Whereas for a cylindrical, meaning for pipes or tubes, the resistance equals to ln R2 over R1 divided by 2 pi KL. That's for conduction resistance. For convection resistance, it's the same in all situations and circumstances, which is 1 over HA. Okay, and all the units are in Celsius per watt. Okay, now let's go ahead and start with the overall heat transfer coefficient for a pipe or a tube. So if we look at this diagram here as a tube or a pipe, this here is the inner radius, Ri, and that's the outer radius. Now, this part here is hollowed, where fluid flows down the pipe, and therefore there's convection in this area here. It's convection, we'll call that convection 1. Therefore, there's a heat coefficient of Hi and an inner surrounding temperature. Okay, should have made it larger, but it's okay. There's also convection here, call that convection 2, and therefore there's a surrounding temperature of T infinity O for outer and HO here. We also have heat transferring in the cylinder here through conduction. So I'll say heat transfer through conduction. Okay, so if I'm asked to find the total heat transfer in this problem here, I'll say that I'll start with Q equals change in temperature divided by resistance. Now the change in temperature, just move this to the left. Okay, the change in temperature is the inner temperature minus the outer temperature, the hotter temperature minus the cooler temperature. So it's the inner surrounding temperature minus the outer surrounding temperature divided by the total resistance. So we have the first resistance inside, second resistance the cylinder, and the third resistance outside here. Therefore, it's 1 over HI plus ln r, the outer radius, divided by the inner radius over 2 pi KL plus 1 over HOAO. Okay? Now, this term here is referred to as the UA product. Okay, which equals to 1 over HIAI plus ln of the outer radius over the inner radius divided by 2 pi KL plus 1 over HOAO. This is what is referred to in the industry by engineers as the UA product. So for example, they'll say the UA product of this heater is this value here, instead of saying this large term. Okay, U itself is the overall heat transfer coefficient. Okay, now therefore this equation can be written as Q equals, instead of this large term, we'll say UA times the inner surrounding temperature minus the outer surrounding temperature, which looks similar to Newton's law of cooling, which equals to HA TS minus T surrounding. The only difference is that this U here is the overall heat transfer coefficient, and this H is the heat transfer coefficient. Okay? Those are the only two differences between the two. And that is your overall heat transfer coefficient. Oh, and one more thing. The heat transfer can be found using both the inner UA product, the inner diameters here, such as the inner overall heat transfer coefficient and the inner area, or it can also be found by using the outer parameters of the UA product, okay? So both methods are right. We'll look into that in the next example in the next class. See you then.